everyone, we are going to do the Unit 5 Part 2 exam review. So Unit 5 Part 2 encompasses all of Unit 5. So this will be, you'll still see torques, you'll still see potentially torque equilibrium, but now in addition to that, you can also see stuff from like Newton's second law and rotation form, and then moment of inertia stuff as well. So let's not delay, let's get right into the problems. A ball of radius r stands from rest and rolls without slipping down a ramp in time t and reaches the final speed, v final, at the bottom of the ramp. Which of the following is a correct expression for the angular acceleration of the ball down the ramp? So we're solving for angular acceleration. Whenever you see rolls without slipping, that usually typically means we're going to use this relation right here or this relation right here. Because when something is rolls without slipping, it's moving translationally and it's moving rotationally, and usually there's a link between the two. And when it comes to angular dynamics, you're going to need this one of those relations between the two. So it reaches the final speed with v final in time t. Let's solve for the linear acceleration based off that information. So we know that v final is equal to v initial plus a times t. The initial velocity is 0 because it starts at rest. So v final equals at, which means a is v final over t. We can then use this equation. Let's solve for alpha. Alpha equals a over r, and then we can plug in our a expression into a right there and get alpha is equal to v final over t over r, or just v final t times r, which is d. Two people are sitting on a large metal disc at a park. Person 1 is halfway between the center and the edge, while person 2 is at the edge. The disc accelerates from rest until it reaches an angular velocity of omega final. Which of the following correctly compares the angular acceleration alpha and the tangential acceleration a of person 1 and person 2? So these two people are spinning on this disc, this merry-go-round, this roundabout, take your pick. Since they are on the same disc, they will have the same angular acceleration. They're both going to be spinning and changing. They're spinning at the same rate. So it's not C, it's not D. So the angular accelerations need to be equal. The linear acceleration is going to be greater for person 2 because person 1 has to cover less ground than person 2. Person 2 has to cover more ground linearly to match with person 1 so that their rotational accelerations are the same. So person 1 has a greater, or person 1 has a less than linear acceleration since person 2 is further out. So the answer is B. The four graphs show the angular velocity omega of identical disk as a function of time t over the same time interval. In which of the graphs is the disk in rotational equilibrium? So this question was actually on your previous exam. I found it fitting to put on your previous exam because it was just torque equilibrium. When we're in rotational equilibrium, just like how we're in linear equilibrium, the velocity is constant. Which of these graphs is showing constant angular velocity? Since we're talking about rotational equilibrium, its graphs 1 and 2 are showing constant angular velocity. Static friction in the hinges of a classroom door can exert a maximum torque of 100 Newton meters. A student can push on the door with a force of 200 newtons. What is the maximum perpendicular distance from the hinges that the student can push the door without the door moving? Okay, so we have this door, and this door is going to rotate about its hinges. So let's pretend its hinges are there. Let's say we're trying to swing open this door there. We are going to apply a force of 200 newtons, and we're basically just asked where do we need to apply this force so that or where can we apply this force to where the door doesn't open. Basically what we're doing is we're just going to solve for the point where the torque from the force matches up with the torque that the hinges need to require to rotate. So friction is holding it back 100 Newton meters. How far in the door will this 200 Newton force exert a torque of 100 Newton meters? So we're just using T equals F times R. So 200 or 100 Newton meters equals 200, and we're solving for R. R is going to be equal to 0.5 meters. So a person can exert this force 0.5 meters away and still not open the door. Let me just make sure I'm getting everything right. D, B, B, C. Okay. Wheel 1 begins at rest and rotates through one complete revolution with a constant angular acceleration of alpha 1 at time delta t. Wheel 2 also begins at rest and rotates through one complete revolution, but with a constant angular acceleration alpha 2 in time 2t. Which of the following correctly identifies the ratio of alpha 1 to alpha 2? Okay, so first things first, alpha 1 needs to be greater than alpha 2. Alpha 1 is getting through one revolution in a time of t. Alpha 2 is getting through one revolution in a time of 2t. So alpha 1 is accelerating faster because it's covering that same ground in a quicker time. So right away, we can eliminate B and A because alpha 1, this should be the bigger number. To get what actually C and D is, let's go ahead and set up our kinematics. We're going to use this equation. So delta theta equals omega t plus 1/2 alpha t squared. We can ignore that part of the equation because it starts from rest. The initial angular velocity is 0 in both cases. So alpha theta equals 1/2 at squared. And let's go ahead and solve for the alphas. Alpha equals 2 delta theta over t squared. For scenario 1, so alpha 1, we get through a delta theta, let's just call that theta, in a time of t. For alpha 2, we get through that same theta in a time of 2t. So we do have to distribute this square, so we get 2 alpha theta, or 2 theta equals 4t squared, or 1/4 2 alpha over t squared. And what we can see is that, okay, alpha 2 is 1/4 that of alpha 1, because alpha 1 is 2 theta over t squared. So rewriting this, we can just say 1/4 alpha 1. So it's a 4-to-1 ratio. Alpha 1 is 4 times that of alpha 2. All right, moving on. Excuse me. Two spheres with a mass of m and 3m are connected by a rod of negligible mass as shown. 3 rotational axes are located or labeled in the figure. Axis B passes through the center of mass of the sphere rod system, which was represented by the dot. Axes A and C are both a distance of d from the axis B. If the same torque is exerted on the system as it rotates about each of the 3 axes, which of the following correctly compares the angular accelerations of the sphere rod systems about these 3 axes? Okay, we know that net torque is equal to I alpha. What we're saying is the net torque for all 3 of these options, where were they? Did it go ABC? Yep, ABC. We're going to spin this object about these 3 axes. The net torque is the same. We want to compare the angular acceleration, so really it just comes down to what's I. The bigger the moment of inertia, the harder it is to get something to spin, so the slower it's going to accelerate. The smaller the moment of inertia, the easier it is for something to start spinning, so it's going to accelerate faster. If this goes down, this is going to go up with the same torque. So basically, we just have to compare the moment of inertias. I know, just conceptually, rotating about the center of mass is always the best way to go. It's always the most efficient way to get the moment of inertia. It's always when the moment of inertia is going to be at its minimum, is when you're rotating through the center of mass. So alpha b is going to be the biggest one. It's going to have the smallest moment of inertia, which means it's going to have the biggest angular acceleration. So alpha b should be at the biggest, which only is in option D, so I don't even have to go further than that. Only D gets that correct. So alpha b is the biggest one. The reason why A and C equal is because now we can go to the parallel axis theorem. When we're doing the parallel axis theorem, both of these are moved the same distance away. So the D's are equal to each other for A and C. And then the mass of the system also doesn't change when we move it to A or move it to C. So we can move it the same distance in both directions, and we'll get the same moment of inertias. A student is provided with the data shown in the table. Does the student have enough information to calculate the average angular acceleration of the wheel? Okay, yes, because the average angular acceleration only depends on the change in angular speed. Yes, because the average angular acceleration only depends on the final values of the angular speed and time. No, because the angular displacement needs to be known along with the change in angular speed. No, because the initial direction of rotation must be known to calculate the change in angular velocity. So, angular acceleration is the change in angular velocity over time. That comes from this equation. That comes from omega final equals omega initial plus angular acceleration times time. We need to, the answer is going to be no. The answer is no, and the answer specifically is D. We can't figure out what the angular acceleration is because we don't know what this initial direction of rotation is. Okay, we have a delta t, so we have a change in time, so that part is good. But we can't find this because we don't know if this is a positive or if this is a negative, because that changes our answer. If it's rotating counterclockwise, so for example, if it's rotating counterclockwise, then we know that we're slowing down because we're going from 3 to 2 radians per second. But if it's going clockwise initially, well, that's a way bigger jump. That's actually a jump of 5 radians per second. So the answer for 7 is D. A disk with mass m and radius r and rotational inertia 1/2 mr squared around its center is free to rotate with negligible friction. A string with negligible mass is wrapped around the disk multiple times, and a small block with mass m is attached to the free end. The block is released and begins to rotate. Which of the following expressions is equal to the tension in the spring after the block is released? So we're solving for the tension in this spring. And we have to solve it in terms of m's and g. So it's seeming like this is going to be a derivation question, so let's buckle up. Let's start off just with a regular free body diagram, looking at this mass. So this mass has a tension pulling up, and it has a force of gravity equal to little mg pointed down. We know that the net force equals mass times acceleration. The net force in this case, I'm going to consider down to be positive, and that also considers clockwise to be positive. The net force is going to be mg minus tension is equal to mass times acceleration. We're solving for this force of tension. So tension is going to be equal to mass times gravity minus mass times acceleration. So here's what our tension is equal to, but the problem is none of these values have acceleration. So that means we're going to have to look at this another way. We're going to have to do something to cancel out this acceleration, and we can find that, what that will be, by looking at the system rotationally now. Rotationally, there's one force causing a torque, and it's the tension going down. So let's look at our Newton's second law in rotation. The net torque is going to be the tension times radius, because the radius is r. The moment of inertia of the disk is 1/2 mr squared. And I'm trying to solve for linear acceleration to cancel out linear acceleration. So let me do this. Linear acceleration is angular acceleration times radius, and then we can solve for angular acceleration by doing a over r, and we can plug that in for this, and we get a over r. Let me make more space for myself. All of the r's will cancel out here. Oops, not the t, the r. And then we get that tension is equal to 1/2 times m times a. Okay, we now have two expressions for tensions, and both of these have acceleration. So let's go ahead and solve for acceleration for one of these, and we're just going to use substitution to get our answer. A is going to be equal, simplifying for a here, it's going to be 2 times t over big M equals a. And now I'm going to plug this in for this a right here. I'm getting a little bit cluttered, but t is going to be equal to mg minus m times 2t over big M. We can now go and just solve for the tension t, but the tension t, we do have to combine our like terms, so let's just start working our way through this algebra. T is equal to mg minus 2 times t times little m over big M. Adding this to both sides, we get t plus 2t little m over big M is equal to mg. And I can factor out a t, doing 1 plus 2m over big M equals mg. And now subtracting on the other side, we get t is equal to mg over 1 plus 2 little m times big M. And so we have an expression for t in terms of what we need to be in terms of. It's not a, it's not b. Okay, maybe we have a little bit more work to do, but I can see that the answer is going to be m over 2 here. It's going to follow this pattern of mg over something plus something, a 1 over something over a fraction. When we factor out mg here, if we factor out big M over g, or sorry, big M over 2, we will get I guess we have to do a little bit more of algebra. We can multiply everything by big M, and we get big M mg over m plus 2 times little m. And then now we can factor out m over 2, and we get m over 2 mg over m over 2 plus m. I ran out of room there, but it's the answer there is D. That was kind of a tough one when it comes to the algebra there. All right, 9. 3 small spheres are attached to a rod of negligible mass that is in parallel to the x-axis and free to rotate about a pivot x equals 0. As shown, the masses and locations of the spheres are indicated in the figure. The rotational inertia of the sphere rod system about the pivot is most nearly blank. So we're just going to solve for the rotational inertia. The rotational inertia is equal to the sum of mr squares. So we have 3 masses we have to account for. The first one, this r is distance. We don't care about what direction it is, so it's not going to be negative, like, for example, a center of mass equation would work, or a net torque equation would work, if we're solving for like torque equilibrium. So we have 0.3 times 0.05 squared we have 0.2 times 0.1 squared, and then we have 0.1 times 0.15 squared. Plugging into the calculator should give us the right answer, so 0.3 times 0.05 squared plus 2 times 0.1 squared plus 0.1 times 0.15 squared, and we get I is equal to 0.023, which is 2.3 times 10 to the negative second. Oops, did I do something wrong? Or did I just plug into my calculator wrong? .3 minus 0.05 squared. Oh, I see what I did. I did plug into my calculator wrong. That's not equal to that. It's going to be this plus 0.2 times 0.1 squared plus 0.1 times 0.15 squared. And we get 0.005, or 5 times 10 to the negative third. All right, that's actually one of our answers there. So, and then the units of moment of inertia, kilograms, meters squared. All right, that was the MCQ. Let's move on to the FRQ. A student wants to test the properties of two spheres, one of which is solid with a uniform density, the other which is hollow, rolling down a ramp without slipping. Both spheres are of mass m and radius r, and both roll down a ramp of length d and angle theta. The moments of inertia of the two spheres are displayed. So we have a hollow and a solid. Based on the information, estimate which sphere, if either, will reach the bottom of the ramp first. Justify using qualitative reasoning. So we have a solid sphere, and we have a hollow one. The one that's going to reach the bottom first is the solid sphere. We've seen this demonstration before with discs. We've seen a disc and a hoop roll down a ramp, and the disc got down the ramp first. The reason why is because the way it's just the mass is distributed is closer to the center of mass of the disc. And in general, when you have mass that's closer to the center of mass of something, it's easier to start to rotate. That is distinguished by its moment of inertia. The object with lower moment of inertia has a better mass distribution and is easier to rotate. So the solid sphere will reach the bottom first. Because it has a lower moment of inertia, meaning it is able to rotate easier. It's less resistant to change in rotation. To change in angular acceleration or angular motion. All right, assume that the net torque on each sphere is a function of the frictional force between the spheres in the ramp. Derive an equation for the linear acceleration A of both the spheres in terms of force of friction and mass. Okay, so looking at, let's do a free body diagram here. So for each of these scenarios, we have something that looks like this. There's our ramp. We have a force of gravity pointed down. We have a normal force from the plane. And then we have a force of friction going up the ramp. What's going to cause the torque is this force of friction. So let's set up a Newton's second law in rotational form. I'm going to do the solid sphere first. So solid. For the solid sphere, the net torque is just the force of friction times its radius. It's this force that's causing the torque. The moment of inertia of the sphere, the solid sphere, is 2/5 mr squared. And then the angular acceleration for the solid sphere We're solving for linear angular acceleration, so I'm once again going to use this connection, and I'm going to plug in A over R for alpha. All of my R's will cancel out. I get force of friction equals 2/5 big M times A. And then A is going to be equal to 5/2 force of friction over mass. And I can stop there because we have it in terms of the variables we need. Force of friction and mass. Our only variables are force of friction and mass. Let's do the hollow now. So same setup. T net equals I alpha. The net torque is still the force of friction times the radius. It's the same for both. The only difference now is that the hoop has a different moment of inertia. It's 2/3 mr squared. And then the alpha, A over R. All of the R's will cancel out, and we get force of friction equals 2/3 big M times A, where A is equal to 3/2 force of friction over M. All right, we've done it. Those are the accelerations for each of the objects. Does the equation you derived in part B agree with your qualitative reasoning? So we said that the solid sphere is going to reach the bottom first, meaning it's going to have a bigger acceleration than the hollow sphere. And do we find that out? Do we determine that? And the answer is yes. This one's, the solids is 5/2 force of friction over M. The accelerations is 3/2 force of friction over M. So the acceleration of the solid sphere is greater than the acceleration of the hollow. And 5/2 is greater than 3/2. So the solid sphere will accelerate quicker down the ramp. And I believe the question was which will reach the bottom first. So let's just add that in, meaning it will reach the bottom first. All right, that is it for the FRQ. Those are all the answers, as usual. If you have any more questions, this one was pretty hard. This one was pretty difficult. The answer is D. I might have messed up my algebra there a little bit at the end or did something wrong, but the answer is D for that one. All right, if you have any more questions, you know where to find me. Other than that, good luck on all your studying, guys. That is it. That is all from me. Bye.